Okay, let's talk through these problems here. So this first one is we want to determine the direction of the magnetic field produced at the labeled positions in the given situation. So we've got a wire here, and the X here means that the current is going into the page. So what that means is that you're going to use the right-hand rule to determine this, and it's going to be the one where you point your thumb and then curl your fingers around. Okay, 1, 2, 3, 4, 5, good. So your thumb is going to be in the direction of the current, and then your fingers are going to curl around in the direction of the magnetic field. So in this case, the current is into the page. So take your thumb and put it right on the X so that your thumb is touching here, and push it into the screen, and that means your hands, your fingers, if it's your right hand, is forced to curl around. So your magnetic field is going to curl around like that. So that means it's going this way at the top, this way at the bottom, at the right, that way like this, and it's circulating around in that direction. Okay, so you'll drag over the proper things into those boxes. So now consider the loop, and the current is going around like this. Indicate the direction of the magnetic field at points inside and outside. So this same thing, you're going to use the same right-hand rule. Point your thumb in the direction of the current. Since it's going that way, at this point, point your thumb in the direction of current. You're going to see that if you push your thumb to the left and curl your fingers, they're going to go into the page over the loop and then come out of the page under the loop. And if you do it here, same thing. You're going to put your thumb in that direction. Your fingers are going to curl around that way and point up here, and same thing, curl in, point up. So in the center here, you'll be able to figure out which direction the current is flowing. Okay, so delete that. Question number 2. Proton with velocity in the positive x directions enter the region where there's uniform in the y direction. You want to balance the magnetic force with an electric force so that the proton will continue along a straight line. Okay, so we've got a proton that's moving in the positive x direction. So it's moving this way. And it enters the region where there's a uniform magnetic field in the positive y direction. So we've got a magnetic field which is going this way in the y direction. So we're going to use the other right-hand rule where you have your 3 fingers, or you can put your thumb in the direction of the proton. So our thumb is going to go along the x-axis. Our fingers are going to go in the direction of the B field, which means towards the y direction. That means the force is going to cause the proton to want to curl down. The force is going to be curled down. So we want to balance that with an electric force. So we're going to want to put the electric force in such a way the force is just Q times E. So we want to counteract that force. So if the force is down, which direction do we need to put the force so that it doesn't go down, it stays flat? Okay. Next question. Determine the direction of the force that will act on the charge in each of the following situations. So you've got a negative charge moving to the left in a magnetic field that points out of the screen. Negative charge moving left electric field that points out of the screen. Okay, so we got a magnetic field, an electric field, positive charge moving downward, and a magnetic field that points upward. So these 3 cases, whenever you have the magnetic field, you're going to use the right-hand rule. For an electric field, whatever direction the electric field is, that's where it's going to push the charge, either up or down, depending on if it's a negative or positive charge. Okay, but the other 2 are right-hand rule, just like we talked about. So a circular flat coil that has N turns, enclosed in area A, carries current I, has a central axis parallel to a uniform magnetic field B, which it is immersed. The net torque on the coil is. So we have a circular coil. Okay, it's got a cross-sectional area A. It's got N turns. There's a current going around the loop, current I. Central axis is parallel to a magnetic field B in which it is immersed. So now we put a magnetic field parallel to the axis. The net torque on the coil is, so if we have a, this is a thing with n turns, so we can think of it like a loop of wire, it's going to generate its own magnetic field. Okay, and so your question is, all right, the magnetic field that it generates is straight up and down, and the magnetic field that it's immersed in is also straight up and down. So what is the torque then going to be on something like that? So just think about what would happen when the magnetic fields are lined up. Okay, a long solenoid carries a current. If the radius of the solenoid were double and all other quantities remain the same, the magnetic field in the solenoid would be, so this just find the equation for the solenoid and then double the radius. What happens to the B if you do that? 6, 2 parallel wires carry electric current in the same direction as shown in the figure. The current in each wire produces a magnetic field, right? Because if you use your right hand rule, point your thumb in that direction, then the field is going to come out of the page here and go into the page there. Number 2, same thing, it's going to come out of the page here and go into the page here. So these two fields are moving in opposite directions at the center point. The question is, blah, 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 blah. In the region of the space near 1, in what direction is the magnetic field produced by wire 2 points? So they're asking about this space. What direction is the magnetic field produced by wire 2 points? So if you put your thumb in the direction of wire 2 and then curl your hands around, you see that it comes out of the page near that point. And that also means that above your screen, the B field is going to the right, and then on the other side it means it's going into the page, and then behind the line through the screen it's moving to the left because it's circulating around this point. Okay, so the question is, what's the direction there? And then what direction is the magnetic force on wire 1 due to the magnetic field produced by wire 2? So if one is this way and the other is that way, so they're in opposite directions, is this going to be an attractive force or a repulsive force? Okay, delete that. 7, 2 parallel wires carry current in opposite directions shown in the figure. So we've got I1 is to the right, I2 is to the left. So which statement is correct? You point your thumb in the direction here, so to the right, so that means it's going to be coming out of the page here, going into the page here. If you point your thumb left for I2, it means this should be an X. It means for I2, the current is also going into the page here and then coming out of the page here. So this will give you the opposite case of the previous problem because they're moving in opposite directions. Okay, charged particle moves in a uniform magnetic field of whatever Tesla with a period of this. Find its charge to mass ratio. So this is the, you're going to use the mv squared over r and then the qvb, and then get those balanced and solve for q over m, and that's going to be, that's the charge to mass ratio, because that's the charge, that's the mass. The ratio means you divide the two. Charge to mass ratio should be mv over br, right? Because you divide by one of the v's, mv over br. And so we've got a charged particle, and mass is q over m, should be v over br. Yep, so then we've got our Tesla, we've got a period of this, find its charge to mass ratio. So based on the period, you can figure out, let's see, the period is the time it takes to go around the circle. So that's related to the radius and the velocity. So you can replace that in and then calculate what the charge to mass ratio is going to be. Okay, delete that. 8, 9. A doubly ionized molecule moving in a magnetic field experiences a magnetic force of whatever newtons as it moves at 311 degrees at some direction angle to the magnetic field. Find the magnitude of the magnetic field. So we've got a charged particle moving in a magnetic field. So it's going 311 meters per second, and then if we imagine the magnetic field here, the direction between them is 72.3 degrees. So find the magnitude of the magnetic field. So this charged particle is QVB sine theta. That's the force on a charged particle moving. So we've got the force here, there. We've got the velocity, 311 meters per second. We've got the angle, and now we just need the magnitude of the magnetic field. The charge of this thing means it's lacking 2 electrons, means it's going to have a charge of 2Q, 2 positive charges. So you can put that in there and then solve for B. Okay, delete. Okay, electron enters a region of space containing a uniform magnetic field. Its speed is 181 meters per second, and it enters perpendicularly to the field. Under these conditions, the electron undergoes circular motion. Find the radius r of the electron's path and the frequency of the motion. Again, there's a plug-and-chug problem. You've got the B field, you've got the V, you've got the circular motion, mv squared over r. What's the radius, and what's the frequency? Again, just look up, there's a set equation for this type of motion. And plug and chug. Okay, elements that appear in the, so okay, we've got a mass spectrometer thing here. So the Ca plus radius here, Ca plus is the top line in this chart here, 0.666 times 10 to the minus 25 kilograms, and a charge of 1.602 times 10 to the minus 19 coulombs. Plug in your 0.352 Tesla magnetic field. Plug that in and solve for the radius using your QE to get your acceleration, and then you can solve to get your velocity right at as it leaves. Once you have that, then that equals mv squared over r, and then solve for the radius there. And then using the same data table, you'll just, based on the charge and the mass, you can plot in the ones that have the biggest radii, and just sort them, so you might have to calculate each of those. Okay, 12. In medicine, it's often important to monitor blood flow. However, the blood flow is difficult to monitor directly. Instead, some medical devices use the Hall effect. Taking advantage of the blood flowing through veins contains a number of free ions. So we want to treat a vein, imagine it to be a rectangle so it's easier to calculate, and we've got a width and a height here. So if you multiply those two, you get an area, and if you've got a certain amount of current flowing through that area, or a number of charges through that area per time, that gives you a velocity and a current. And the magnetic field is immersed, that the vein is immersed in, has a strength of 0.0755 Tesla. It's pointing horizontally and parallel to the width. Okay, so there's your B field. It's going into the page, basically. Suppose that medical precautions mandate that the speed of blood flow for this particular component of the body should never drop below 16.9 centimeters per second. At what minimum Hall voltage in millivolts should the medical device be designed to trigger an alarm to the medical staff? Okay, so they're trying to measure blood flow using a Hall effect device, and they want to have it trigger an alarm when the flow rate drops below 16.9 centimeters per second. Okay, so that's going to be you need to balance this QE and the QVB together. So you've got the ion traveling to the right, you've got the strength of the B field, and then that is going to create a charge separation with an EMF, and then the EMF from the top to the bottom of this thing is going to create a separation of the charges, and then that's going to create a net force that pushes the electrons over. And so what you want to solve for is the EMF that's going to balance out the forces to keep it at 16.9 centimeters per second. If you do that, then what happens is if your speed drops below 16.9 centimeters per second, the charge will no longer be balanced. The EMF will get larger, and then bling, 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 your alarm is going to go off. Okay, so there's the balance equation for the. There's a really good example of this in the book. Talks specifically about a blood flow, and just follow that example. Okay, so you got a wire of length L. It's conducting current top of the page through a magnetic field directed into the page. So we got a wire going straight up and then a magnetic field going into the page. What's the direction of the magnetic force on the wire? Okay, well, you do your ILB, force on a current carrying wire, and then calculate what the force is going to be from that. We just have I, we have L, we have B. They're perpendicular to each other. So you just multiply them all together. Okay, that's the force on a current carrying wire by an external magnetic field. So now we've got a 149 turn current carrying loop immersed in a magnetic field. The area of the loop is that. The angle between the magnetic dipole moment and the field is 49.7 degrees. Find the strength of the magnetic field that causes a torque to act on the loop when a current of 0.00351 amps flow in it. So we have a 1, 2, 3, 4, 5, 6, 7, right? N equals 149 turn solenoid, basically, or doesn't have to be a solenoid. It could be my eraser's not working. It could be a very tightly wound. There we go. A very tightly wound. A very tightly wound loop too, of 149 turns. Okay, and it's immersed in a uniform magnetic field. We've got the area of the loop here. We've got the angle of 49.7 degrees. Okay, and we want the strength of the magnetic field that causes a torque of this to act on it. So we've got a torque, and then we've got a current I. Okay, and then we've got the area, and the area is pi r squared. So we can solve for the radius, and we're going to need the radius because there's our loop and there's our radius here, and the axis of rotation, or the distance, the torque that's going to be applied is at a distance r away from the loop. So we need that distance to calculate our torque. So then you can solve for what B is in order to cause that torque. Okay, so same type of thing, force on a current carrying wire, except now we multiply by distance, L or R or width or whatever, in order to get our torque. Okay, so delete that. 15. Current in a long straight wire produces a magnetic field of 1.29 microtesla at a certain distance from the wire. Find this distance. Okay, so this is just mu naught I over 2 pi r, or whatever the current for a current carrying wire is, the equation for that is. So you've got a wire. The question is, you've got 6.21 amps flowing in it. Point your thumb in that direction. Then your hands are going to show that it's coming out of the page at the top and into the page at the bottom, down in front of front of the wire, and up in the back of the wire. Okay, and if you're a distance r away, the field gets weaker with r, and at that point it's 1.29 microtesla. So B is mu naught I over 2 pi r, something like that, for the magnetic field for just a wire. At any distance r, the magnetic field strength will go down. Okay, so delete that. 16. Find the magnitude of the magnetic field at the center of a 33-turn circular coil with a radius of 16.1 centimeters with a current of whatever. Again, plug and chug. We've got a n turns, radius 16.1, so we can calculate the B field of at the center of a circular loop. It's just like the B equals mu naught I over 2 pi r, but in this case it's for current in the center of a loop. Number 17, a current of 6 amps in a solenoid of length blah creates a Tesla, 0.205 Tesla magnetic field at the center of the solenoid. How many turns does the solenoid contain? Again, plug and chug. Put in your current, put in your radius of your cylinder, you calculate the area if you need to, or whatever you need to do, and then you've got your B, and then solve for what n necessary to do that, the number of turns. So just so you understand, we've got a solenoid. Okay, solenoid is just a loop of wire, continuous loop like that. In this case, we've got 13.6 centimeters, and we've got n turns, so usually you need to do n over 13.6 centimeters, something like that, to get your density, and then plug that in for your equation for a solenoid. All right, now we got 20 amps flowing in a long straight wire. Find the strength of the resulting magnetic field at a distance of 50 centimeters from the wire. So same thing. We've already done that problem. I should delete that because you've already done it. When operated on a 110 volt line, typical hairdryer drives 1450 watts of power. The current can be modeled as a long, straight wire in the handle. During use, the current is about 2.05 centimeters from the user's hand. What's the current in the hairdryer? So you've got P equals IV, so you can solve for the current. What is the resistance of the hairdryer? V equals IR, so you can solve for R. What magnetic field does the hairdryer produce at the user's hands? So this is going to be a long handle with a straight wire, and then you've got B is mu naught I over 2 pi R, and you can calculate the strength of the magnetic field that your hand is going to experience just from the current flowing through the wire. Two long parallel wires carry currents of 1.09 amps and 4 amps. The magnitude of the force per unit length acting on each wire is that. Find the separation distance of the wires expressed in millimeters. So we have two parallel wires, and then you can solve the magnitude of force per unit length. You can look up the equation. They've got F per L in there, and then you can just solve for the separation between them because that's one of the variables. Plug and chug. All right, 21, two long parallel wires separated by this. Find the magnitude of the force that acts on either one on a 3.83 meter length of either wire. So that's, again, it's the force between two parallel conductors. It's just an equation to plug in and chug. The figures here show snapshots of a rectangular loop as it passes from left to right through a region of a constant magnetic field. The field points into the screen and is perpendicular to the loop. In which of the sequence is the magnetic flux through the loop decreasing? Okay, so what you're trying to do is, as you're moving the loop into the magnetic field, think about, what is happening to the magnetic field in that box. Is it getting bigger? Is it getting smaller? Obviously, in A, there's no magnetic field in the box, and in E, there's no magnetic flux field in the box, which means no magnetic flux. Okay, so play around with that. Copper ring of radius R in the figure lies in a magnetic field pointing into the screen. The field is uniformly decreasing in magnitude. The induced current in the ring is what? So we've got a copper ring, radius R, in the magnetic field. The field is uniformly decreasing in magnitude. So if the field is decreasing in magnitude, what happens to the current in the ring as you have a change in magnetic field, which means you have a change in magnetic flux inside the wire. So this is a Faradays Law or a Lenzs Law. What happens to the current in the wire? So remember, your EMF in the wire is equal to d phi dt, okay, or proportional to that change in flux over change in time. So the area is not changing, your wire's not changing, but the magnetic field of strength is changing. So what's going to happen? 24, two metal rings with the axis are placed near each other like this. If a current IA is suddenly set up and it is increasing in the ring A as shown, the current in ring B will be what? So you put up a current here, suddenly a current starts flowing there. That means you put your thumb in the direction of that current, and that means the magnetic field is going to flow like this. So if a magnetic field suddenly starts flowing like that, okay, and so now we're suddenly getting a magnetic field flowing through that other ring, what's going to happen to the current in that second ring? Think about Lenz's law. Okay, for each case here, indicate the direction of the induced current in the wire loop. A velocity vector drawn near the magnet indicates the magnet is moving, and the velocity vector in the loop shows the loop is moving. Okay, so so again, this is Faraday's law of induction or Lenz's law. You're pushing magnets. So you've got a magnetic field like this, and these pictures are right out of the book. Basically, you can copy what they say there. It should be pretty easy. But we're increasing the magnetic field. We're pushing it in. And if we're pushing it into this thing, then the current generated is going to be create a magnetic field that's going to be opposite to that direction. So the current should be going around, I guess that would be counterclockwise. So if you put your your thumb in the direction of the current, your fingers curl around, and the magnetic field points down through the center of this thing. So it should counteract the north that's coming into it. Okay, and then you'll do that for each of these and just work through that. Okay, 26. A simple bar magnet is held as shown, aligned with the central axis of a circular coil of copper wire. If the magnet begins to move, electromagnetic induction will result in the coil of wire exerting a force on the magnet. As the magnet moves to the right, in which direction will the resulting force on the magnet act? So again, what we're talking about here is Lenz's law. You're pushing a magnetic field in. It says it begins to move. It doesn't really say. So as it moves to the right, what's going to happen, right? And if it moves to the left, what's going to happen? So again, Lenz's law. If you move to the right, the flux will decrease. If you move to the left, the flux will increase. So what does that mean for the EMF induced in the wire? Okay, a permanent bar magnet, south pole pointing down, is dropped through the solenoid, show in the illustration. What is the direction of the induced current that would be measured in the ammeter as the magnet falls completely through the solenoid? So in the first case, think about this. So as it falls in, the flux is going to start to increase, but from the south pole, and then as it falls through, as it comes out here, that south pole, the opposite thing is going to happen, and then the north is going to pass through. So what's going to happen to the current? Think about it. It's pretty fun. Okay, and then delete this. And then will it show the same reading the whole time, or will it flip as it falls through? And if the, and you can think about it, do d phi dt here at the top, d phi dt at the bottom. Assume they take the same amount of time. You can make up a time there and just think about what would happen to, is the flux as the south enters into it, and then there's a moment where the flux is constant because along between the north and south pole the field is constant. So it should do one thing and sort of settle out, but then as north comes in it should do another. So think about that. Okay, if the magnet still oriented with the south pole pointing upward is pulled completely downward through the solenoid, what is the direction of the induced current measured in the ammeter? What is the direction? If the magnet still oriented with the south pole pointing downward is pulled upward completely through the solenoid. Okay, so now you're just pulling it up rather than pushing it down. So think about that. If the current through an inductor were doubled, the energy stored in the inductor would be, okay, so just take the equation for energy stored in an inductor, double the I, and what do you get on the other side of that? Okay, in the circuit shown, the capacitor is fully charged when the switch is closed at time t. Consider the plots A through F. Which plot describes the energy stored by the capacitor and inductor as a function of time? So these are just straight out of the book. You can just pull those up. 30, for an LC circuit, when the charge on the capacitor is 1/2 of the maximum charge, the energy stored in the capacitor is, so again, just take the equation, put in 1/2 for one side of the equation. What do you get on the other side? 31, uniform magnetic field of 4.5 Tesla points in some direction. Consider the magnetic flux through a large triangular wire loop, 3 equal sides of 1.15 meters. Area of that would be 1/2 base times height. So it would be 1/2 that squared since they're equal sides. Determine the maximum absolute value of the flux. So the maximum absolute value is going to be 90 degrees if the magnetic field is perfectly lined up. So the flux of that is just B times the area. So your 4.15 Tesla times the area, 1/2 base times height of your triangle. That's going to be your magnetic flux. Now it wants them in Webers or Webers, so you have to convert it from Tesla to Webers, and you can have Wolfram Alpha to do that. In the minimum, you shouldn't have to do anything. You should be able to tell what that is. Okay, we've got our magnetic field passes through a horizontal circular wire loop at an angle of this. Find the magnetic flux, BA cosine theta. Simple. Area pi r squared. Go for that. We've got TMS treatment, a transcranial magnetic stimulation. We put an external magnetic field, 5 Tesla, very powerful, using external coils to zap the brain a little bit. During the treatment, the current rises from 0 to the peak current in 70 microseconds. Assume that the magnetic field is uniform over a circular area of diameter 2 times 10 minus 2 meters inside the brain. What is the magnitude of the average induced EMF around this region of the brain during the treatment? So you have your area. Your flux is going to be B times the area. and then the change in magnetic field is going to happen in 70 microseconds. What is the average EMF? So the EMF is going to be 0 to 5 teslas times that area divided by 70 microseconds. That's your, should be the EMF induced in the brain. Okay, you've got a circular coil. It's got a radius immersed in a magnetic field perpendicular to the plane of the coil. You've got your 0.121 seconds. The magnetic field strength increases from this, so that's your change in magnetic field. So your flux is going to be 92.1 minus 55.7 times the area divided by 0.121 seconds. And your area is going to be 2.97 centimeters, so you're going to multiply that all by 101, and then make sure it's asking you for millivolts, so make sure you put that in there. All right, so the component of the external magnetic field along the central axis of a 49-turn circular coil of radius 29 centimeters decreases in 1.2 seconds. If the resistance to the coil R is 4.5 ohms, what is the magnitude of the induced current in the ohms? So you're going to do the same thing you just did, calculate EMF, but then V equals IR, so then you can solve for what I is given the R and the EMF that you generate. What is the direction? So then you use your Lenzs Law for that. Okay, an astronaut repairing the outside of her ship accidentally pushes away a long steel rod, flies off, never to be seen again. The rod is oriented perpendicular to the magnetic field in that region of space. The rod is moving perpendicular to its length as well as to the direction of the magnetic field. Magnetic field strength is 7.33 millitesla. What is the magnitude in EMF in millivolts induced between the ends of the rods? So then you've got a 98.9 centimeter long steel rod. You've got a velocity. And so you're going to put that as if it's flying through the space, through that magnetic field, and then calculate what the EMF is as it changes, as it moves through that magnetic field. Okay, 37, you've got a wire moving to the right at the speed of 8.3 meters per second, 2 parallel wire rails connected to the left side shown in the figure. The whole apparatus is immersed in a uniform magnetic field. What is the EMF in the wire? So again, this is just a plug and chug. The induced EMF causes a current to flow in the circuit formed by the moving wire and rails. In which direction does the current flow? Just grab your book and copy the arrow out of it. Let me see. And then in which direction is it? If the moving wire and the rails have a combined total resistance of 1.15 ohms, what applied force would be required to keep the wire moving at the given velocity? Assume that there is no friction between the moving wire and the rails. Okay, so you'll want to calculate using the resistance, the current, and then what you'd have to do to balance that out so that it would keep it moving. Okay, you've got a rectangular coil, okay, sides, so there's an area, you've got an end there. If it's rotated about a long axis in a uniform magnetic field of 0.53 Tesla, at what frequency in complete cycles per second must the coil be rotated for it to generate a maximum voltage of 1.15 volts? So you're going to go to the motor section of your book, and this thing is going to rotate at a certain frequency, given torque. You've got the area, you've got the flux going through it from the magnetic field, 0.53 Tesla, and then there's an equation that has the motor frequency, and there's just solve for F there. Okay, this guy, Tarek, winds a small paper tube uniformly 179 turns of thin wire to form a solenoid. The tube's diameter is 9.69 millimeters and its length 2.37 centimeters. So again, you're going to want 179 turns per 2.73 centimeters to get your turns per centimeter. What is the inductance in microhenries of Tarek's solenoid? Just plug that into the equation and solve for that. But again, make sure you put little n in instead of big N. Okay, a large circular loop of radius B has a current I passing through it. The loop is held horizontally with its plane parallel to the ground. A much smaller circular loop is also held horizontally in the plane of and concentric with the larger loop. Determine the formula for the mutual inductance M of the two concentric coplanar loops. I think I'm going to delete this problem. This is not a good problem, so I'm going to delete that. Don't do that one. 41. Experimentally, the magnetic flux in a solenoid was measured for various currents. The data was recorded in the table and plotted in the graph. The best fit line through the data was also shown. So we've got our current, we've got our magnetic flux, and we see there's a plot here. What is the inductance? You can try to measure the slope of this line, which is rise over run. So if I were to do it, I would find a point on the line that is easy to locate, and that might be something like this point here, because that's 1, 2, 3. Well, that's at 1, and this is 1, 2, 3, 4, 5. So your rise is 5, your run is 1, 5 over 1. That can help you out there. Okay, delete the screenshot. 42. You've got your inductor, blah, blah, blah. Calculate the initial current at t equals 0 seconds. As soon as you turn it on, what happens in your circuit? You're going to have current flowing. What's going to happen? Calculate the current as time approaches infinity. So as this thing gets set up, what happens? And then you plug it into your equation at t equals 2.39 seconds. Plug it in there, and you can get your current there. So you should just take your equation for current in an RL circuit, and just look at it and put t equals 0 in. What do you get? Put t equals a really big number in. What do you get? And then what do you get at some specific 2.39 seconds? And then determine how long it takes for the current to reach half of its maximum. So that's just, you can eyeball that one. All right, 43, or just plug in half in for your solve for t with current equals half, 0.5. All right, so we're considering an RLC circuit. You've got R and C in there, but we don't know what L is to find its value. And Ninja decides to perform some simple measurements. He applies an AC voltage that peaks at 36 volts and observes the resonance angular frequency occurring at omega of 15,300 radians per second. What is the inductance of the inductor in millihenries? So again, this is a plug and chug. Put in your 855 ohms, your 2.25 microfarad capacitor, your AC voltage of 36 volts, and then solve for what omega is. Okay, 44. What is the inductive reactance of a 40 microhenry inductor placed in an AC circuit driven at a frequency of blah? Again, plug it in, chug it in. Same thing with this. What is the capacitive reactance? So just make sure you're reading what inductive reactance and capacitive reactance is. And then 46. We've got a capacitor is fully charged when the switch is closed. Calculate the time needed for the potential energy stored by the circuit to be equally distributed between the capacitor and the inductor. Capacitance is this, inductance is that. Solve for the time when the energy is half, so you can set the energies equal to each other. Okay, 47. Yep, plug and chug. Consider a series RLC circuit where the resistance R is this, the capacitance C is that, and the index is this. Determine the resonance frequency omega 0 of the current, of the circuit, sorry. Again, plug all that in, just solve for omega 0. What is the maximum current? What is the maximum current when the circuit is at resonance if the amplitude of the AC driving voltage is 36 volts? Again, just plug that in, check that in. So we got a Hall probe trying to measure the magnetic field strength. One such probe consists of a pore conductor, 0.155 millimeters thick, whose charge carrier density is 1.17 times 10 to the 25 cubic meters per cubic meter. When a 1.07 amp current flows through the probe, the Hall voltage is measured to be 4.57 millivolts. What is the magnetic field strength? So then just go to the Hall probe equation. If you just plug all this stuff in, solve for B, that's it. Okay, 4950. On which variables does the magnetic flux depend? The magnetic field, oh yeah, anyway, so you can figure that out. A typical wall outlet in the United States is 120 volts. MP3 players typically require much smaller voltages, typically 340.9 millivolts. If the number of turns on the primary coil is 2,464 turns, calculate the number of turns on the secondary coil of the adapter transformer. Okay, so we're trying to take 120 volts and turn it into 340.9 times 10 to the minus 3 volts, and we've got 2,464 turns on the primary coil. So solve for, you put the V1 over V2 equals the primary over secondary, the relationship there between the two things, and just solve for N number of turns on your secondary coil in order to do that, in order to step that down. So again, transformer is really cool. You just have a wire coming in, looping around, leaving another wire coming in with fewer, and you can turn 120 volts into 10 volts by borrowing only some of it with the fewer turns over here. Okay, anyway, that should do it. Okay, see you guys later.